Good afternoon, everyone. Today we're going to go over the first part of controls, which we've actually been doing in the DF2 architecture. And even when we're talking about the, oh, wow, Karan, you almost had me. I almost, I caught you out of the side of my eye. Yeah, that's great, man. I love that movie. Yeah, you got me. um, so anyway, um, so I have a lot of notes and things. Um, the the Google Doc notes, right, are here where I just put the links to the existing notes. But then what I've been doing is trying to summarize things, right, to almost as if this is your, developing your equation sheet for the exams. All right. And before we get started, just so you don't get confused, we'll render those equations. All right. Um, so control theory. So, control systems, it's the automatic controlling of things, right? It's not the person doing the things. So without automatic control, the modern world wouldn't really exist. Now, yep, you're a control system and you have a lot of sensors and you can operate in parallel and process signals in parallel and believe it or not, for the amount of calculations your brain does, actually very low power, right? Really, the amount of power we use is kind of independent of how hard we're thinking. Really, the power we use is just to maintain our body temperature. Okay. Now, you can get humans to do things for you, but they do get bored. Personally, I don't like to work in radiation contaminated environments or environments that are on fire or environments that are too hot or too cold or too far away. Right. And so it's great to have an automatic system to do that for you. Also, as great as humans are, our reaction time is 8 seconds. Um, so you could almost think of that as 5 tau for a human is 280 milliseconds. All right. But yeah, automated control systems, right? They can save time, money, can save lives, but they take away jobs, right? And if you remember Charlie and the Chocolate Factory, right? A robot put Charlie's dad out of work, fitting caps on the toothpaste. Now the movie ends well because they needed somebody to service the robot. Now, that kind of one-to-one job creation doesn't exactly exist. Now, and the thing is that the original job, the cap putter on her, that job is gone. Right now, it's the maintenance of that robot. The thing is Charlie's dad might have to perform maintenance on 20 robots, right? So there's kind of one job created, but 20 toothpaste cap putter honors lost. However, there's a lot of jobs created in the design manufacture of the robots, and the problem can be is if in the United States it can be hard to retrain to a new job, but but really we've lost more jobs to automation than to any competitor. So now, control systems, they do not have to be electric, right? Or they certainly weren't electric before. Think of that where the faster it spins, these balls swing out, which pull this lever up, which reduces the flow of air, which makes the engine go slower, which then the balls come down, right? Homeostasis, oops, is a control system on the human body, right? Or an organism's body, and maintains your body temperature and things like that, right? Um, most like Now, even though we're going to talk about continuous time systems for control, right? A lot of control is done with something called a microcontroller, which um, some of you are in 120 and you're using a TI product. Some of you have had EE30, which should have been a Texas Instruments microcontroller, but they might have switched it around for a little bit, right? But they're like, mini CPUs, but they're kind of meant to read in and read out signals. Now the thing is in courses like EE 138, which is control system microcontroller systems, right? It is digital. However, when I look at the exams, they all look like they're based on 110 continuous time systems. All right. So even though microcontrollers are used, the things that they're controlling are in the real world and tend to be analog or continuous time in nature, right? And a lot of things that we do are, you know, a power supply is in fact a control system, right? Even you might think it's simple, make a 5-volt power supply, but a 5-volt power supply that delivers 5 volts when the load is changing wildly, right, can be a challenge. But um, you know, how's this work? Is that is that we have some kind of system, right? And it's called open loop because there's no feedback from this output to that output. However, that transfer function inside might have a feedback loop that you don't see. All right. Now, an example of an open loop control system might be your outside grill, right? When you set the fire on your outside grill and set it to half, the temperature goes to some value. And you might think, well, it goes to a constant value, so it's in control, but not really. The reason why it reaches that value is that the heating and the cooling settle at some value and you reach a temperature, right? And if you turned your grill to the same level on a really hot day or versus a day at top of Mount Lassen, you would that final temperature is more a result of the outside ambient air rather than actually controlling it. Right. Now, what you're probably used to is if you have heating or air conditioning, right, you just set it to some value that you want it to be. Right. It's supposed to be 78 degrees for, yeah, 78 degrees is the recommended temperature, right? Um, and that the system would be some kind of heating or cooling, and then you have a temperature sensor in the room, which then is fed back into the controller, right? So that it basically and you've probably seen this, is that the heating goes on, it reaches a temperature, and then the heat goes off. Then the heat goes on, and then the heat goes off, right? And so mathematically, we have this system diagram over here where we have the input, and this is really the output, right? Whatever it is we want to set. And now we've added this feedback system, which is something, a function of S. Now we've already done this with op amps, where the transfer function was something that modeled the gain bandwidth, right? And then the feedback was two resistors, right? Which we called beta. And so we took a system that was one thing and then turned it into another. But remember that open loop gain, AVOL, right? Meaning there's no feedback. So that's the open loop gain. Now, so what you're going to be doing is deciding what kind of GS is needed to turn an out of control H of S into something that is controlled, right? Now, let's talk about what does being in control look like, right? Now, this is like a working definition, is that if you put in a step input, the output will eventually settle to a DC value. Or now a step is defined as 0 going to a value. But really, if you start off at any DC value and change to another DC value, that system will eventually go to some DC value, some constant value, right? So that's what it looks like. So if you put in a step response and it oscillates or it increases, and does anything but settle back down to a DC value, it's out of control. All right. So let's take a look at this transfer function, 1 over S, right? The inverse Laplace transform of that is the integrating function. So if I do the convolution, so this I could just replace with convolving with UT. All right. So let's take an example of G of T. So green is UT. The red is this triangle, right? And we find the the common is a step times a ramp, right? We then take the inverse Laplace transform of the common function and then scale and delay. And this was like an example off of one of the midterms. And so the blue is the output. It starts, it increases, and then it goes to some DC value. But it's not in control because the input is making it go back to 0. Okay. So the input, it might make you think it's in control, but really it's not. All right. So let's just do if so if G of T was an RT, a ramp, right, and you convolve that, we get some kind of squared, and so it keeps increasing, right? Now, yeah, if you put in, a ramp into a system in control, the output will keep going up, right? Now, let's just do the step, right? So if I have H of T as a step, right? And then the input is a step, and in this case, I've delayed it. The output is a ramp, right? It never settles, so it's out of control, right? And I can do things like have a step and then it keeps bending, but really integrators integrate. And if you put in um, a step response, it'll just keep integrating to some linear thing, right? Now, that's just one way of looking at it, right? So the real mathematical rule is that poles cannot have a real part equal greater than or equal to zero. Or the real part of the poles have to be on the left-hand side of the complex plane, right? And so in this case, the pole of this is zero, right? So let's, before we go too much further, so let's just draw the complex plane. All right. This is j omega, right? That's the imaginary part. And then here we have the real part, right? So having a pole here, right? We can see that there's one pole, right? I don't know what, well, actually, I know that the denominator would be a constant because I haven't put a zero anywhere, right? I don't, I don't know what that constant is, but I just know that it's a constant, right? And I know that if I just call that a, right, and it's minus a, that the transfer function will be s plus a. And what's the inverse Laplace of this, right? It's something e to the minus at, which is exponential decay, right? Even a step function of a low pass filter has exponential decay in it, right? And it goes like that, right? So any system that's in control, right, has exponential decay there. All right. So now if I put a pole at zero, right, well, that's h of s equals, and again, I don't know from this diagram here, right, is that, which gives us our integrator function, right? Now, another issue is I could have a pair of complex poles, right? And the transfer function of that would be some kind of constant s squared plus omega naught squared. And that would be plus j omega naught and minus j omega naught. Where does that come from? Well, let me look at the quadratic equation, right? A equals 1, B equals 0, C omega naught squared for AC to A. Well, when I substitute everything in there, I get plus or minus J omega naught, right? Because that's 0. And so that's a negative. So it'll all be there. Now, What's the inverse Laplace transform of this, right? It's some kind of sine, right? Which is an oscillator, right? So if I put a step response into this, right, I'm going to get some kind of sine wave. So the value never settles to a DC value, right? So it's out of control. What if I have, right? I have a pole here. Well, the transfer function of this, right, is actually some constant s minus a, which the inverse Laplace is proportional to e to the plus at, which is exponential growth, right? So you can have one pole at 0 and it's an integrator, and you can have multiple poles at zeros and they'll just, so if I had two pairs of poles at 0, I'd have a double integrator. 3 poles at 0, triple integrator, right? If I have a pair of complex poles, then it's an oscillator, right? And then if I have any pole on the right hand side, right, or greater than 0, right, I am going to get some kind of exponential increase, right? Now, let's just take a quick review down memory lane for over, under, and critically damped systems, because now's a good time for that, right? Is that, and now I'm strictly talking complex second order systems, right? So now I have 2 poles, right? Some constant, right? S plus A, S plus B. So both of these are going to get, there's 2 real poles that are different. They're on the left-hand side. And so that's overdamped, right? I can do this and say now there's 2 poles at the same value. Right? Now this will give me something with t to the minus at, right? But still, that exponential decay is stronger than a linear function of t, and so this will settle to some DC value, right? And that's critical, critically damped. Now, so the A's and B's aren't these A's and B's. It's just the real part is the same, right? And these are the complex conjugates of each other. So I have plus BJ and minus B times J, right? And this is going to give me some kind of, it'll give me but it'll also have an oscillating term. Okay. So, but regardless, this will, all 3 of these will eventually go to a DC value. right? Now, what if I had a pair of complex poles here, right? This oscillates, right? Forever, right? This will eventually go down to zero, right? But what if it was here, right? It will take a lot longer time to damp down to zero. And so what if I was even close? In this case, minus t, right? That's 5 tau is 5 seconds, right? But what if it was 0.1, right? What if 5 tau was 100 seconds? It would take 100 seconds for this to stop oscillating, right? And so that might seem like forever. And be careful, because some people will call things with too many oscillations, they'll call it unstable, right? Even though the real part will be on the left-hand side, it's these oscillations are too high and too long to meet your specification. So but in this class, I will just go by the strict mathematical definitions, right? But as a control systems engineer, people might use the terms unstable when they really mean an underdamped system with a small value of zeta. And zeta would be, if you recall, you have some numerator, s squared plus 2 damping coefficient omega naught s plus omega naught squared, right? And just another word on n of s, right? If n of s equaled omega, right, that'd be our low pass. If it equaled s squared, that would be high, right? I have I would put a 0 here. That now I'm telling you that the numerator has 2 zeros at that point, right? If I had excuse me. Two zeta omega naught, that would give band response. And if I had this as the numerator, that would give me the notch pass. But the denominators would all be the same. Now the thing is if this term is missing or negative, or if this term is somehow missing, right, then it's out of control. And there's no low pass out of control system, no high pass out of control system. No matter what causes it to be out of control, it's out of control. We don't give them special names, except, right, I guess the two special names would be pole at 0 is a integrator, right? And pair of complex poles, binary poles, are an oscillator. All right. So the thing is you could be given you know, right? Systems are, and really, I could put S here, right? In this case, I could put S squared. It doesn't matter. The denominators tell the tale, right? And so, this is out of control because the pole at zero acts like an integer. And so a step response keeps increasing. This acts like exponential increase. So step response of that is an exponential increasing function. And this has complex, purely imaginary poles. And so the output is a sine wave. And that's why it's out of control, right? But with the second order systems, right, there's a few, like all right. So right, all of these are the same sign, it's in control. All of these are the same sign, it's in control, right? And all the terms are present. S squared is there, S is there, and S to the zero is there, right? So these are the things when looking at a second order system that you can rapidly determine that what's missing or what you need, right? So if you had a transfer function like this, right, you'd say, well, where's the S term? I need a new function that does something that adds this in there, right? If I had this, right, well, that's really just this, which puts a pole at zero, right? But there's a missing term. We have to add that. And yes, you could have S squared minus AS, right? And you have to add something, and you have to make that sign positive, or make the other two negative. All right. But if you really want to know what the poles are, just use the quadratic equation, and you can see, does the real part greater than or equal to zero, right? If the real part is less than zero, it's considered in control. Oh, sorry, I just saw the chat. Andrew, yes, the lower part is this, the real part is the sigma. Right there. Sorry, I got to talking. Um, So, but it doesn't have the pictures associated. Okay. Now, the next part is like, okay, you can tell if a system's out of control. You can tell maybe what needs to be done, know how to fix it, right? And these feedback networks have special names. And if it's just a constant, it's proportional. If it's an integral, it's some constant divided by S. If it's derivative feedback, it's just S times some constant, right? Because the inverse Laplace transform of 1 over S is integration. The inverse Laplace transform of S is a derivative. But then you can put them together. You can have proportional plus integration, and then you just need two different values for the constants, right? And you can have proportional plus, and then you can have proportional plus integral PID control, right? Which I bet some of you have already heard of that, right? Setting those constants, though, is not a trivial task. There's it's a lot of tweaking. All right. So so now let's try to put this all together. To have a system that acts like an integrator, right? But, you know, I need it to be in control. Okay. So let's just put this block. I have some input, right? But if I convolve a step with that, right, I'm going to get a ramp. It's going to be out of control. So we need to apply negative feedback. We don't know what it is, but it'll be some transfer function, right? Yeah, I'll put that here, right? So here's our in, here's our out, and now V out over V in, we give it a different name, Q of S. Right? Well, let's just go through that again. V out, right? V out is V in times H of S. But also, if I follow V out, that gets multiplied by GS. It's inverted, and it's multiplied by H of S. So now let me collect the V out term. All right, so there's the negative, but when we bring it over on the left-hand side, it becomes positive. That's why the negative feedbacks always have a positive sign. All right, now we find V out over V in, and we get H of S. right? Now, yeah, you can plug in your H of S and your G of S, but there's actually kind of a shortcut that I want to show you now. And let's just go up here, and that the transfer function has a numerator polynomial and a denominator polynomial. All right. So now let's substitute that. And I'm going to do it in more than one step because it can be a bit confusing at first if I just draw it out. Okay. So there, now I've substituted it. But really, I could write it like this directly. All right. So I multiply through the numerator, and that's still the numerator. Right? I multiply through by ds, and I have the original denominator, which was the thing that was out of control. We multiply through by here, though, the denominators cancel out. And now I have the numerator times G. This is the new, right? So Q, the denominator of Q of S is the original denominator plus the original numerator times that feedback network. Okay. Adjust G of S to get all poles on the left-hand plane. Okay. So that's I'm writing this almost directly, like, so the example was 1 over S, right? So the original transfer function was 1 over S. That means the denominator was S and the numerator was 1. So now I just like, oh, what was the numerator? 1. Denominator S. Original numerator 1 times G of S. Okay.
Professor Parrott?
Yes, sir.
Can we use this this as like a general rule for like homework and tests and so forth?
I hope so. That's why I'm showing you, right? Yeah, I'm
Awesome,
it because yeah, that's what I hope I'm showing you. Yeah. Yeah.
Okay, yeah, I was just asking in case you wanted us to go through the entire so finding the VL, moving it over all the general algebra.
Huh. Well,
you know, in my that,
homework, I get, yeah. Okay. All right. Now I get you. Now I get you. I think it's the old comment, show your work, right? And you don't want to run afoul of not showing your work. Well, to me, after drawing the picture, right? Well, right here, I mean, the first step would be, why is this out of control? It's out of control because there's a pole at 0. But really, that's only half the story. You can just say that, right? Poles at 0 are out of control because when you integrate a constant, you get an increasing or decreasing function that never settles to 0, right? So therefore, it's out of control, right? the thing that they're looking for it to be in control is that it settles to a DC value, right? And for a DC input. And so that's really a DC input is some kind of step because you have to turn the system on at some point where you're changing the temperature or the speed or something at some point, right? So just saying that a pole is at zero doesn't, thing that's going on. Well, right, it's the integration. That's fine. What I will say, oops, is that people who do this step first quite often get it wrong. And people who do this straight off the bat tend to get it right. I don't see people going straight to this so often. I wouldn't have marked. And what I mean is, is that for whatever reason, if they're doing this, maybe they're a bit confused, or maybe they make an algebraic mistake or something, right? It's kind of that, with the Bodie plot, right? I'll say s squared plus s plus 10, and some people will transform it to 1 over 10. Right? S divided. People make a mistake doing that and then get it wrong, right? So I just try to minimize. So that's just what I've noticed. But again, it's not a hard and fast rule, right? But if you started here, I'd be fine. If you started here, I'd be fine. If you started here, that'd be fine. If you started there, I'd be fine, right? I think even if you start here, you don't run out of time. Okay. And let's just even have a quick review. What I've noticed is some people, when they do this problem, oops, they'll try to do it maybe, let's say, EE98 style, where, IR1 equals IR2. Then they'll do, let's see, that's 0 minus the XR1 equals PX R2, and then V out equals open loop gain V plus minus V minus. And then you substitute things in, and then let open loop gain go to infinity, and then you get 1 plus R2 R1. People who start off like that and just don't remember that the gain is this, they tend to run out of time. Okay. So there's some things that you just have to have cold, right? So, like, this is that it doesn't look like if you started here, people are running out of time. It just looks more like you're making a mistake. And that, sorry if that was a little more preachy than maybe what you wanted, but I'm just trying to, give you tips. Okay. We all good with that? Okay. So we've gone through all of this, right? I can even spray this. Okay. So now I have to ask myself, what is going to make so I have choices, right? I have K, k divided by s, sk, right? So, these are my choices: proportional, integral, derivative. All right, so let's just try it. S plus 1 times k. Well, if k equals 0, I'm right back where I started, right? If k were less than 0, I would have exponential increase. And so really, k has to be greater than 0. I'm not telling you what it has to be, but it just has to be greater than 0. And then we're going to get exponential decrease. All right, next one. All right, well, this is not in the right format, right? So you have to have the polynomials in descending order, and you can't have it inverted. So let's just multiply the numerator and the denominator by s. Okay, and we get s squared plus k. Now, the s term is missing, right? And what that means is, on the quadratic equation, that b squared term is gone, and I'm left with 4a is 1 times k, and now I have imaginary roots, a pair of them. So that's going to be an oscillator. So now no matter what, and then yeah, if I set k equal to 0, I'm right back to where I started from, right? And let's see if I can get a little more room. What if we selected g of s equal to sk? Okay. 1 times sk. So now we have 1 over s plus sk. So we pull out the s, 1 plus k, the pole is still at 0. So we just have a different scale version, but it's still an integral. Just let me finish the thought and then I'll get to the chat. So anyway, when I look at it, I realize, what's missing, right? I need some positive integer, right? And the only thing that's going to give me a positive integer is proportional, right? But I showed you that by doing the others, that it would still be wrong. Oh, okay, thanks. Okay. Now, so far, I haven't had any. So let's say, what if I had s my, all right, that's a little bit different. All right, so I have my feedback, right, goes into h of s, g of s, subtracted, right? And I know that q of s is going to equal my old numerator, my old divided by my old denominator, plus the numerator times g of s. Okay. And yeah, I'm doing that because, we can, I have to go over it each time. That'll be less examples I can get to. So what is the numerator? S. What is the old denominator? S minus a. The old numerator is S and G of S. All right, so this is the part I have to worry about, right? So S minus A plus S G of S. Well, what was the original problem? That minus A, right? There's a root, there's a pole on the right-hand side, right? So it, it doesn't meet our mathematical definition of being in control, because that the inverse Laplace transform will be proportional to exponential increase. So this is the issue right here. We've got to make that into a positive number. So minus A plus S times some function, right, to be greater than 0. Well, let's go through let's try K, right? So minus A plus S times K. Well, you have to add, so if this has no term in S, I can't add SK. That's only going to affect that term over here. So that's not going to work, right? Let's try SK. So minus A plus S times SK. Well, that's S squared. Well, now I've turned it into a second order system, but still I'm not changing that, right? So really, what if I tried K over S? All right. So I have minus A plus S, right, times K divided by S. Oh, now they've canceled out, right? And so right? And so then, so if I just look at the whole thing, I have S minus A plus K, right? Because I've canceled. Originally we had S, but then we multiplied that by K divided by S, so we're left with K. What makes this system have a root on the left-hand side? K being greater than A. Okay. And notice we had a different numerator, right? And the numerator is unchanged, right? But now we're in control.
Wait, Professor.
Yeah.
So can you go back to QS? Yeah, so it's in control because K is greater than A, is that what you said?
It'll be in control if K greater than A. So if A is 10, K has to be greater than 10. If A is 1,000, it's got to be greater than 1,000.
And that makes it in control, this
right,
QS.
because this will then be a positive number and you'll have exponential decay, right? This will be minus A plus K T. So if K is less than A.
Oh, okay, I get it now. Okay.
No, this is backwards. Sorry. Yeah, I see.
Okay, I understand why.
Oh, that's good.
Thank you.
That's good. Thank you for telling me. So, now here's the thing. I can ask this question. Can't ask, right? So in this case, right, I have two poles at 0, right? Oh yeah, I guess I could ask something like this, but I'm not gonna. All right. Anyway, two poles at 0. And so that what's going on if I look at my rules, right? Well, there's the S term is missing, right? And the constant term is missing. All right. So whatever I do, I know that something's going to have to be here, right? So yeah, it's two poles at 0. That means double integration. And so if the integration of a ramp of a step is a ramp, well, then a double integration that is a ramp square, right? That's scaled appropriately. So Q of S, and now, right, I'm just going to write it straight out. The original numerator, the original denominator, plus the original numerator times G of S, which we have to select. Oops. Okay. So, what's missing here, right? I need something to the S, and I need a constant. So GS can't be just one thing, right? So it's easy and easier because I just multiply it by 1. So G of S, right? Well, it's going to be K, right? Because 1 times K gives me the constant value. But now I need something times S to give us the S to the first power. So K2 S, right? Then that gives us, right? And if you look at now what will make all the roots be on the left-hand side? Well, the signs all have to be the same. So these have to be greater than 0. All right. Now, as a what if H of S equaled -1 over, it doesn't really matter. Okay. Even if this were -1, right? I wouldn't make that positive and turn that minus, right? You would just keep the minus sign up there. Okay. Now, yeah, where would positive gains come from? Well, Non-inverting op amp would give you a positive gain, right? A buffer would give you a gain of 1, and that's certainly greater than 0. Okay. All right. So there's actually two things wrong, right? There's an S term missing, right? And that's got a negative sign. So this is going to be some kind of, could be an exponentially increasing oscillator, right? But we've actually got two problems to fix. There's the original numerator. There's the original denominator plus g of s times the original denominator. So now we need to make this positive, and we need to get just a regular s term in there as well. But notice we're s squared, right? So s squared is what I have to work with. Well, if I do s times s squared, well, that's s cubed. If I just do k times s squared, well, that doesn't really, it gives me more of this. It doesn't give me anything else. Right? Now, if I do k divided by s squared, yeah, I'll get k s. Great. Okay, there's my missing s to the first power term. But how do I get this down to a constant? Well, I have to use a double integrator. All right. So I have to take whatever the numerator is and take k of s and manipulate it until I get what I want, right? So now, after we've done that, s squared minus c, I'll call this one k1 and this one k2. So I have plus s squared k1 divided by s squared plus k2 divided by s. So s squared comes through here plus k1. S squared comes through here, I get plus k2. I rearrange it so that it's easier to see. Right? And so if we remember, right, everything has to have the same sign. The terms are all there, right? What's going to keep it positive? Oh, k2 greater than 0. What's going to keep that positive? K1 greater than C. So if these two conditions are met, right, then you're fine. It's in control. right? Now, something I want to point out about higher order systems. Okay, it's true. A1 all the A's must be greater than 0, right? Because if any one of these is 0, you've got a missing term, and they all must be positive, right? However, there's more conditions to make the control. So if all the A's were 1, you could have a pole, you will have a pole on the right-hand side, or you'll have an oscillator or something. So if I had to, if let's say I had a system, something like this was minus, this was missing, this was missing, I would say, well, I want to make that positive and I need to add something, but the exact values that I use, it can't just be greater than 1. There's more to it. And learning all that is EE 132. And there is a way to do it. There is a mathematical procedure to come up with those constants to make it in control. But it's more involved than we need to get into in 110. We're just getting the beginning. So on the exams, if you see something higher than a second order, you're just going to tell me what's missing, and in general, the approach you're going to take. I have to add something, things need to be positive, right? But if you see a second order, no, those you can use those rules that I gave, right? But integration, right? Or I should say real, right? Imaginary poles, right? They oscillate, right? And poles greater than 0 have exponential increase. So those are the Y's. Oh, there's a pole at 0, it's an integrator. The input will increase or decrease forever. Imagine, oh, there's a pair of complex, there's a pair of imaginary poles. The output's going to be an oscillator. We got a pole greater than 0, we're going to have exponential increase. So that's the Y, right? That's all the Y. And then there's the fixes that you have to do. All right. Next time we'll do more examples. Okay. But this is I'll answer your question in a second. But this is the last topic for the second midterm, right? We'll have something on DF2, which is essentially negative feedback, right? But we're using op amps. We have something to do with gain bandwidth, which we get into the op amp and negative feedback and not having negative feedback. We have questions on the Fourier transform. We have mass spring damper, and then we have this control. So those are your 5 questions. Yeah, Gerardo, exactly. It's missing B of S and C. Or one was even negative. Yeah, yeah, no, it meant, yeah. You were right, Gerardo. All right, what's your other question? Somebody was having a question?
I was just wondering if you could restate what we're supposed to do if it's a higher order than 2.
Basically, make sure that every term is there. And as a start, every term is positive. However, that's not, it's necessary, but it's not sufficient. Coming up with the relationships of those constants for higher order, it's like another 2-day lecture. Okay. And that's really EE 132, right? Even though we do talk about higher order things for DF2 and in lab, you know, really we spend a lot of time on second order functions, really. Okay.
Okay, thank you.
Okay. All right, everybody, have a good day.
Just
Good
one
day,
last
Professor David.
question.
Oh, all right.
So in the numerator, is it just not very important what's in the numerator?
Well, the numerator is what gets multiplied by G of S to fix it being out of control. But the numerator itself, doesn't. Okay.
Sorry, could you repeat that again?
I'll put it in 110. You don't really have to worry about the numerator.
Okay.
The numerator times G of S is the fix. However, a real op amp has a transfer function more like this, which again, that's just a negative sign, and we just have a 0 that's not at 0, right? And you get a function that the magnitude of this kind of looks like that. All right. And we have A much bigger than, or no, it's the other way around. A is a lot less than B. Okay. But what can happen if I put this into a negative feedback loop, right? What's a negative feedback loop? A buffer, right? So let's do that. Here's my numerator. I put it there. Here's my original denominator. Here's my original numerator. What's G of S? It's 1. And notice that minus B can take a stable system and now turn it unstable. And so I have to do something here to make sure that this doesn't give me a pole on the right-hand side. Okay. Now, what we do is that most op amp manufacturers, they put a pole on the inside already for you that makes sure that that doesn't happen. Okay.
Mhm.
This is very high level stuff. You won't really see it until 124. Okay. But so that's when I say in 110, the denominator is just the thing you use times G of S to fix the instability.
Okay.
Okay. This is true too, but I know that if you see a minus and a minus, oh my God, all hell will break loose on an exam. So, and I don't want to do that to you, but you might see it one day. Okay.
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 And
Good
just
question.
for like technicality, in the numerator, there's a S plus A minus S minus B. So
Yeah.
in the new denominator, there would be no S term. And how would that like play out?
I'm thinking, so this one I'm kind of going off of memory. And there's another term there.
Okay. Okay. Yeah. Yeah. That's fine.
Okay.
I was just wondering.
Okay, there, no, no, it's true. You're right, but right, because here, this, you'd see something, you'd see one ramp, then you'd see this, so that's like minus 20, minus 40. No, I have to go.
Yeah.
I have to go and
It's
do
okay.
that one. But what I'm saying is that these kinds of things can cause issues when you simply hook it up, right? Not only will it, now, yeah, we have questions where hooking it up like this takes a overdamped system and turns it underdamped, right? But if the transfer function is like this, it can take an in control system and turn it out of control. Okay.
Okay. So if
again,
there's like an additional zero on the top, then
Yeah.
it will completely change it.
It's still the same process though.
Okay.
What I'm saying is if you're like me, if you y equals mx plus b, and if somebody said, well, now we're going to do d equals c times z plus y, I'd be like, what the hell is that? I wouldn't know what you were talking about just by changing the variables. So this one, right, on an exam is just a little too far away from what we know to really test if you know the control, the basics of control systems.
Okay.
You know what
I
I'm
see.
saying?
Yeah. Yeah. I understand.
Yeah. Okay.
Okay. All right. Thank you so much.
All right. Thanks for coming. All right. Take care, everybody.